Good morning. So we discussed with the division algorithm again, but we want to look at the same theorem from a different perspective, okay? So let me just remind you what was the division algorithm. This tells you that if a is an integer, b is also an integer, and moreover b is not 0, then there exists a unique q in Z, and there exists a unique R in Z, so that A is equal to B times Q plus R, and moreover R should satisfy this condition. So that was the division algorithm, and then we started, we actually presented some examples how to use them to mainly find remainders. But now let us look at this problem from a different perspective. The perspective that I want to consider is to use this algorithm to partition the set of all integers into different categories. Okay? So probably the simplest one is, for example, let me choose B to be 2. Okay. And then let me just rewrite this algorithm once more. So what does it mean? It means that whatever you choose from the set of integers, according to this theorem, can be written in this form, so that A is equal to B, but this time I have chosen B to be 2, so this becomes 2Q plus R. So first of all, you might ask why you have chosen 2. You have to be patient and you will see why, okay? But for the time being, let me rewrite this theorem this time for B equals to 2. And then A, any number that you like. I don't have any restrictions on A, but I have chosen B to be 2. Then according to this algorithm, this A that I have chosen can be written as 2Q plus R, but moreover, R satisfies this condition, yes? It should be greater than or equal to 0 and less than absolute value of B, but I have chosen B to be 2, so it becomes 2, yes? Yep. But then we know that R is also an integer. We know that R is supposed to be on this in this interval. So how many choices are there? This means that either R is 0 or R is 1. Yes? So then it means if R is 0, then what do I get? I get that A is 2 times Q. If R is 1, this means that A is 2Q plus 1. But this is actually very, very trivial fact that you know even from primary school, yes? What is the meaning of 2 times Q? Q is an integer. If you multiply it by 2, it becomes an even number, yes? But here, if you multiply Q by 2, it becomes an even number, and when you add it, it becomes an odd number. So that's a very, very trivial and simple fact. It means that any integer that you choose is either, because there is an or here, is either even or odd, which is very, very trivial, yes? So this means that if you consider, I don't know if this is a good picture or not, but let me just use it as a metaphor. So assume that this rectangle represents Z, and if I choose B to be 2, this will actually partition this set into 2 pieces, but they do not have anything in common. So when you say I partition a set into subsets, into subcollections, it means that I divide the set into 2 groups or some number of groups. In each group is not empty. The whole becomes the whole set, and there is no intersection, there is nothing in common between these two parts. So it means that this part is viewed as 2q, if you want to have a visualization of that. So it means that these numbers on one of these parts are 2q's, and the other one are 2q plus 1s. Okay, so here there is a name for it. This group we call them even, this group we call them odd. Yes. So this means that any number in Z is either even or odd. Yes, as simple as that. But now let me choose, let me go further. So this was very trivial. But now let me choose B to be 3, yes? If I choose B to be 3, what happens? Then if I rewrite this theorem once more for B equals to 3, and I just choose A randomly from Z, whatever I like, then according to this theorem, A can be written as 3 times Q plus R, but R should be somewhere between 0 and 3 this time. So how many possibilities are there? This time 3 possibilities, yes? So either R is 0, or R is 1, or R is 3. Oh, sorry, R is 2. Okay, and then again, if R is 0, then A is 3 times Q. If R is 1, then A is 3 times Q plus 1. And then if R is 2, then you have A equals to 3Q plus 2. Yes? So what does this mean? It means that any number with respect to 3 has 3 possibilities. Yes? Either it is a multiple of 3, or it is a multiple of 3 plus 1, or it is a multiple of 3 plus 2. So any number that you choose in your head from a set of integers falls into one of these categories, and only in one of them. Yes? Or in other words, you can say that any number that you choose has remainder 0 when you divide it by 3, or remainder 1 when you divide it by 3, or remainder 2 when you divide it by 3. So there are any number that you can guess. For example, I don't know, so just randomly 25, for example. So what is the remainder of this by 3? It is 1. So because you can write it as 3 times 8 plus 1. So you see that any number that you choose should be of these forms. One of these forms exactly. Yes? So any number that you choose is either a multiple of 3, or a multiple of 3 plus 1, or a multiple of 3 plus 2. Any number, any integer that you choose. And then you can immediately, so if I want to have this picture, so I have the same Z here, but if I choose 3, then I can partition to the Z into 3 categories. One category is all the multiples of 3. One category consists of all multiples of 3 plus 1. And the other category is this one. Yes? Any questions so far? Okay. So for example, now I can choose these numbers differently. Yes. So for example, let me just write one more. So if I consider B to be 4, then let me just make it simple. So how many possibilities I have for an integer A? So how many? So I choose A in Z. I fix B to be 4. I choose a number, arbitrary number from the set of integers. But this A, with regard to 4, has 4 possibilities. Either what? What are the possibilities? Yes? No, A itself. Yes, but about this problem, yes, yeah. Yes, so with 4q, so it is 4q or 4q plus 1 or 4q plus 2 or 4q plus 3. So these are the possibilities that I have for A. So this means that, yes, you are right. If I divide A by 4, the remainders are either 0, 1, 2, or 3. Any number can be any number that you imagine from the set of integers is either a multiple of 4, or a multiple of 4 plus 1, or a multiple of 4 plus 2, or a multiple of 4 plus 3. So Q belongs to Z. Yes? So, for example, if I want to consider this, that's also instructive to have this. So if I take it 4 parts, so if I choose 4, I am partitioning Z into 4 pieces. So the one part is 4q's, 4q plus 1, and 4q plus 2, and then finally 4q plus 3. So look here, when I chose B to B2, I partitioned Z into 2 groups. One I called them even, and the other one I called odds. And then here you understand that what type of number are these numbers? Are these numbers even or odd here? These are even. But these are also even. Do you agree? Because that's a multiple of 4 plus 2. And this part is odd, and this part is also odd. So this means that if I consider 4, then with regard to 2, numbers are even or odd, but with regard to 4, numbers are they have those 4 options. But if I ask you even numbers, how can you write an even number so that this, instead of 2 we have 4? Then you say that this is not completely clear. The even numbers fall into 2 categories. Either they are multiple of 4, or they are multiple of 4 plus 2. And odd numbers are also either 4q plus 1 or 4q plus 3. So anyway, any number that you choose will partition Z into that many groups. The important thing is that realize there is no mixture between groups. So you cannot find a number that belongs to both of these groups simultaneously. They are completely separated. They are disjoint subsets of Z. This is the terminology we use if they are nothing in common, okay? Okay. So this is the content. So another perspective of this division algorithm. For the time being, do you have any questions regarding this? Okay. Now let me give you an example. So example, show that, I hope that this question is understandable now. Show that the product of 2 integers of the form uh, 6q plus 5 is an integer of the form 6, for example, k plus 1. So now this is not, so I hope that by reading this sentence it makes sense to you, yes? So the product of 2 integers of this form. So you know that here B has chosen to be 6. So how many categories we have? If we choose 6 for B, 6. And then what are they? 6q, 6q plus 1, 6q plus 2, up to 6q plus 5. So yes, that's one possibility, yes? So this means that if you want to visualize what is the problem is telling you, so you know that the numbers are either 6q or 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 and finally 6q plus 5. So these are possibilities that I have. And this is telling you that if you choose 2 numbers from this category, from this part, multiply them, it becomes a number, but it lives here. Yes, and for example, can you give me two numbers, small numbers that we can multiply in our head of this type? Give me two integers of that type, 6q plus 5. Oh, this should be simple, yes? In a matter of seconds, you should be able to tell me. Give me two numbers of the form 6q plus 5. So you choose q, for example, to be 1. Then it gives you 11. You choose q to be, for example, 2. It gives you 17. Yes? So 17 and 11. So 11 is definitely in this group, in this part. 17 is also definitely in that part. Yes? Is that clear? Okay, now let us multiply them. If you multiply them, it becomes 187. Yes? But this claims that 187 belongs to this part, because it is 6k plus 1. K is an integer, okay? So let us check. So if I divide this by 6, so how many times? 31. Yes? 6 times 31 is 186. But I need 187. So I need to add one more. So you saw that I took two numbers from that part, multiplied them, it became a number, and I then check it. I realized that it is in the form of 6k plus 1. Is the question clear? But we want to show that this is not random, because I chose random numbers from that group. It worked. I want to show that this is not a coincidence. It will work no matter which pair you choose from the last part. Yes? So how should I prove that? I would say that, okay, let me choose a number from this group. So let me call it 6q plus 5. Let me choose another number from this group. So what should I write for that? I should write 6q prime plus 5. Yes? So this is one number from that part. That is another number from that part. I can, of course, choose q and q prime the same, but that is not always the case. So I am separating the names. And then I start multiplying them. So what will happen? It becomes 36q prime. And then the next one becomes 30q. The next one becomes 30q prime. And then finally I will have 5 times 5, 25. Yes? So I started multiplying this by that, this by that, this by this and that. Yes? But then, can you tell me what to do? Because my goal is to show that this number, no matter how complicated it is, I want to show that this is of this form. I want to show that this number definitely belongs to this part. So in order to show that, I should show that this is a multiple of 6 plus 1. And this is very, very simple. You have enough experience of that. What I'm supposed to do for 25? Yes? Yeah, so how should I factor 6 out? Because 25 is not divisible. Exactly. So this motivates you immediately to write it as 24 plus 1. And now 24, 30, 30, 36 are all multiples of 6. So I can pull a 6 out. Then it is 6q prime. And then I have 5q. And then I have 5q prime. And then I have 4. And then at the end I will have plus 1. Do you agree that this is an integer? Yes, because q and q prime are integers. So that combination is definitely an integer. So I can call it little k in the problem. So this becomes 6k plus 1. So you see that it doesn't matter which numbers I am choosing from this part. As soon as I multiply them, the result, the product, will no longer be that in that group. It jumps here. Okay, let me ask you one question. So if I write some integer like this, for example, 6a minus 2, or minus, let me write 5. So what type of number is this? Because you know that according to this algorithm, any number that you just write should be one of these forms. Okay, but I have intentionally written 6q minus 5. So 6 cubed minus 5 is not one of these forms, but according to this theorem, it should we should be able to write it in exactly one of these forms. Now my question is that which form is this? 6 cubed minus 5 is which one of those forms? Yes? 1. Yeah, exactly the same thing. So how did you write that? You write 6 cubed. Instead of this one, you write what? Minus 6 plus 1. Yes, and then you factor 6 out, and then you have q minus 1, and then plus 1. And instead of that one, for example, you can call capital Q plus 1. So you see that if you write this number of this form, if I ask you in which part does this one belong to, you will say that this is also in this part. Yes? So every number, every integer can be written in one of these forms. There is nothing specific about 6. There is nothing specific about 3 or 2. For the case of 2, we have something more. We know what they are called. They are called even and odd numbers. But for the case, I don't know what is this called. You can say it's a multiple of 6 or multiple of 6 plus 1. But they are not famous as even and odd. Yeah. Anyway, any questions here? Okay, so for example, let me give you some very simple ideas how we can use them. So can you show me, or can you argue for this? If I give you 3 consecutive integers, then you can guarantee that one of them, and exactly one of them, is divisible by 3. Why is that true? So I give you a list of consecutive integers. I imagine a list of 3 consecutive integers, but you don't know which list I have, but you can say something. You can say that whatever list you have in your head, exactly one of them is divisible by 3. Why is that? Of course, you might be trivially, it's very obvious for you, but you have to have a good reason for that. So 3 consecutive numbers, when I say, what do I have? One of them is A. The next one is a plus 1. The next one is a plus 2. Yes? But I don't know what a is, but I am telling you that exactly one of them is divisible by 3, no matter what you have chosen for a. Why is that true? Because you say that for this a, how many possibilities are there when it comes to 3? 3 possibilities. This a is either 3q or 3q plus 1 or 3q plus 2. There are no other options, yes, for a. Okay, if a is of this form, I am done. Why? Because so if this is this case, what is my list? My list will be 3q, 3q plus 1, and 3q plus 2. If a is 3q plus 1, then this becomes 3q plus 1. The next one becomes 3q plus 1, 1 more. The next one becomes 3q plus 2, 1 more, yes? And then if this is the case, my list is 3q plus 2, 3q plus 3, and 3q plus 4. Yes? Now see. So what this is important. Are there any other possibilities that I have to consider? This is the important thing of division algorithm. Division algorithm tells you that don't worry. If you consider this, and that, you have considered all scenarios. There is nothing left. So if you can prove your statement for this case, and that case, and that case separately, it means that you have been able to prove your statement for the whole integers. Yes, that is the important thing. So, and this is very simple now. If this is the case, do you see in my list there is exactly one of them which is divisible by 3? The answer is yes. Which one? The first one. If A is not of this form, but it is of this form, then I will generate this list. Now, can you see in this list exactly one of them is divisible by 3? Which one? The last one. Why is that? Because I can factor a 3 out. So it becomes a multiple of 3 again. If A is of this form, then I will have this list. Then which one is multiple of 3? The middle one. Yes? So it means that regardless of the value of A, because A is either of this form or that form and that or that form, and I was able to show the truth of this statement for each case, it means that I was able to prove this. Is that clear? Yes or no? Yeah. By the way, what type of number is this, 3q plus 4? Because when I say which type, I expect you to tell me one of these types. Yes? Because this 4 is bigger than 3. So when I say 3q plus 4, it means, yes, plus 1, because you can write it as 3 capital Q plus 1. Yeah, so this is, I want you to be quick and understand what is going on. So any questions here? Okay. Now let me see if we have more interesting examples. For example, I would say that n is an integer. Okay. We want to prove that 6 divides this combination. So I am claiming that whatever you choose for n, if you calculate this combination for what you have chosen for n, it becomes a number which is definitely divisible by 6. Yes? I want you to understand it becomes a little bit lengthy, and I'm not telling you this is probably the best way or the most efficient way to do it, but it is exactly one way, and this will this will give you a good idea of how to use this division algorithm here. So how do you think I can do? So because I want to show that this is divisible by 6. So which number becomes more relevant if I want to use this theorem? Because you know that when I ask you, you can write the division algorithm for 2, you can write the division algorithm for 3, for 4, or for any number that you like. Okay? So for solving this problem, which one is probably a good natural starting point? Do you think I should choose B to be 2, 3, or what? We want to talk about, yes? 6 is probably the most natural one. Might not be. So let us just choose 6. So it means that this n that you see falls into one of these categories. Either it is 6q, or 6q plus 1, or 6q plus 2, or 6q plus 3, 6q plus 4, and finally 6q plus 5. Yes, I know it is actually very lengthy. Very lengthy, it means that you need to consider 6 different scenarios. But what is the meaning of this? It means that, first of all, how many options are available if you wanted to check them case by case? Infinitely many, because I have infinitely many integers. But using this theorem, I am trying to actually reduce this problem into a problem with only 6 stages. And if I succeed to show this is true for each one of these cases, because these cases are the only possible cases, it means that I have already shown that this is true. Is the logic clear? Okay. And then, of course, it is very simple. Do you agree? If n is 6q, it's very trivial. Because when you say n is 6q, it means that this... So let me just write it. No. So this combination, it becomes 6q times 6q plus 1 times 6q plus 2. Do you agree? If n happens to be 6q, then this product takes this form. But now look, I can call this capital Q, and then you have a multiple of 6. A multiple of 6 is divisible by 6, so I check that this one is valid. Yes? Now I go to the next one. If I go to the next one, n times n plus 1, n plus 2, what happens for this? The first one is 6q plus 1. So what is the next one then? It becomes 6q plus 1 plus another 1, so it becomes 6q plus 2, and then multiplied by 6q plus 3. Okay, but then what? because I want to have a multiple of 6. It is not that clear yet it is a multiple of 6. So why this is a multiple of 6? Hello? Why it's a multiple of 6? Because you can factor a 2 here and a 3 there. 2 times 3 is 6. Yes? Isn't it simple? So this one is 2, 3q plus 1. This one is 3, 2q plus 1. Yes? And then this 2, then that 3, multiplied, it becomes 6. And then I write the rest. 6q plus 1. Yes? And then I have 3q plus 1. And then I have 2q plus 1. First of all, do you agree with my algebra? So what I did, I chose this one and put it in this equation, in this expression. The first one becomes 6q plus 1. The next one is 6q plus 1 plus 1, which is 6q plus 2. The next one is 6q plus 1 plus 2, which is 6q plus 3. But my goal is to show that, again, this is a multiple of 6, which is not that clear from this way of writing. Then I realized from the middle one I can factor a 2 out, and from the last one I can factor a 3 out, and then 2 times 3 becomes my 6 that I can write it from in the beginning, and I copied and pasted this part, copied and pasted these parts. And then, so this is my algebra. But what is the conclusion out of my algebra? This time I can give this the name capital Q, because that is definitely an integer. And then again I have my multiple of 6. Is the logic clear or not? Okay, but then this means that even in this case, I was able to solve the problem. Yes? Let me do it once more. I just want to skip these parts. I want to ask your opinion. It might happen that this is my n. So let me write it here. If n is this one, so then n times n plus 1 times n plus 2 is equal to n is 6q plus 2. So what is the next one? 6q plus 3. And what is the next one? 6q plus 4. Do you agree? But do you still see your multiple of 6 again? For example, you can factor a 3 from here and a factor of 2 from here. So what will be? The factor will be a factor of 6. In this case, you can also factor a 2 from there, and then you will have a multiple of 12. So this, in this particular case, this is divisible by 12 as well. Yes? But not in all possible scenarios. For example, it was not clear from the beginning. In this case, I don't see how can I make a factor of 12. In this case, I don't see how can I make a factor of 12. But in this case, it is also a factor of 12. Automatically, it also becomes a factor of 6. But what matters for me is to show that this is a factor of 6. Yes? Yes. No, you shouldn't, yes, you shouldn't lose your goal. Your goal is to show the right-hand side is definitely divisible by 6. Yeah. In some cases, it might be divisible by multiples of 6, which in this case, that's also true. But for example, in this case, if n is of this type, definitely this product is divisible by 12, but this is not always the case. It was a coincidence for this scenario. So then I hope that you agree with me. I don't want to write it. So this is also a multiple of 6 at the end. Okay, so, and then of course this is done. I have to consider these cases. So here, if I have 6q plus 3 for the first one, so I already have my multiple of 3, and the next one becomes 6q plus 4, which gives me a multiple of 2. So this is again multiple of 6, and this one and that one you can check easily. For example, let us check the last one. If it is 6q plus 5, okay, the next one is 6q plus 6, and then you have your factor of 6. That's done. So it means that you have to be patient to do all for all cases. But it is much better than considering infinitely many cases. The whole point is to understand after this step, I want you to understand that really you have a proof, because there are no other possibilities for an integer, and you have already considered all possibilities, so it means it is done. This logic I want you to understand. Yes? Okay, let me give you another example. Yes? No, if I give you this example in the exam, then you have to be patient and write all of this. Yes, yeah. But I will not probably. Okay. So let us try to go to another example. And by the way, you might find an alternative here. Do you see an alternative? If you want to prove a number is divisible by 6, one possibility is to actually talk about 6 itself. But another possibility is, if you want to say, by the way, you might know from Grundschule which number is divisible by 6. This is a rule of thumb. If you want to know if a number is divisible by 6, yes? Yes, or in other words, no, that is a yeah, but I mean easier. That is what you said is completely what I'm going to say. Yes, yes. 2 and 3. So if you want to see if a number is divisible by 6, one idea is to show that this number is simultaneously divisible by 2 and 3. Yes? Okay. But now let us do it quickly in our head. Okay? Is this number divisible by 2? Because n is a number. It is either even or odd. If n is even, the whole combination is even, and it is divisible by 2. If n is odd, the next one is even, and the combination is an even. So as simple as that. So I showed that this is always divisible by 2. Yes? Can I show this is also divisible by 3? The same story here. If I have 3 consecutive numbers, exactly one of them is divisible by 3. So from one of these, exactly one is divisible by 3 as well. So definitely this combination is divisible by 3 because of what I just told you here. And it is divisible by 2. So it is divisible by 6 as well. Yes? That's also an alternative. I just want you to be able to understand. I don't care about if you write them in detail, but I want to get you to develop a sense or a feeling for how to calculate these things quickly. Understand the problem. Yes? Okay. So now let me give you another example. So show that the remainder of the square of any odd integer by 8 is 1. So is the question clear? I'm saying you that if you have an odd number, any number that you like, square it, divide it by 8, the remainder out every time becomes 1. So, for example, let me choose another. So let me just choose 3. It's an odd number. I square it, it becomes 9. I divide it by 8. The quotient becomes 1. How much is the remainder? 1. It's not a coincidence. For example, 5 to the power of 2 is what? 25. You divide 25 by 8. You multiply it by 3. But what is the remainder again? 1. So it's not a coincidence. So this tells you that any odd number you choose, square it, divide it by 8, the remainder is always 1. Okay, I want you to prove this, okay? I want to wait a little bit for you. Okay, any ideas? So which number you are choosing for your B here? Yeah, 8 is the natural one, but my recommendation, be lazy always. Because if you want to go to 8, then you have to consider 8 cases. Definitely it will work. Okay. Okay. By the way, do I really need to consider 8 scenarios? Why not? No, by the way, that's also a good thing that you mentioned this one. Can I say a number is divisible by 8 if and only if it is divisible by 2 and 4, as I did for 6? I told you that a number is divisible by 6 if and only if it is divisible by 2 and 3. Can I say the same thing for 2 and 4? Yeah, the answer is no, but can you give me an example? A number which is divisible by 2 and 4, but it is not divisible by 8. Yes? Yeah? 4 itself. 4 is divisible by 4, it's also divisible by 2, but it's not divisible by 8. If you think it's too trivial, give me another example. Yes? 20 is divisible by 2, it's divisible by 4, but it's not divisible by 8. So be careful. The case for 2 and 3 was, this is working for 6 because there is no common factor between 2 and 3. Yes? There are no common factors between 2 and 3. So if a number is divisible by 2 and simultaneously divisible by 3, it is enough to conclude that it's divisible by 6. But if a number is divisible by 2 and it is divisible by 4, because 4 itself is 2 times 2, there is no guarantee if a number is divisible by 2 and 4, it's also divisible by 8. Sometimes it is, sometimes it is not. So this is not a good way to do it. Okay? So let me talk a little bit around that. So in principle, the first number comes to mind because of this experience we have is just to write this number with 8 scenarios. So I would say that let n be an odd integer. So let me write a, not confuse you. Okay, let a be an odd integer. Okay, then, of course, in general, how many cases are there for a? A can be 8q or 8q plus 1 or 8q plus 3, 2, 8q plus 3, 8q plus 4, 8q plus 5, yes, 8q plus 6, 8q plus 7, yes, in general. So in principle, when it comes to a and 8, I have 8 scenarios going on. But now I have told you here that a is odd. So this means that you need to cross this out, yes? Because when a number is multiple of 8, it is automatically a multiple of 2. So it is even. So an odd number cannot be, in general, yes, any number can belong to in one of these categories, but in this case that a is odd, a cannot belong to 8q plus 1, 8q. It cannot belong to 8q plus 2, because 8q plus 2 is also an even number. So I have to cross this. And then the same story for 8q plus 4, 8q plus 6. So this means that the situation is slightly better. So instead of considering 8 cases, I need to consider only 4 cases. Yes? Is that clear? So this means that if you write it in that way, that's completely acceptable. So you consider this case, square it, and show that the square is of that form. And then this is not finished. You have to do the same thing here, the same thing here, the same thing here. For example, let me choose this one. Then what is a squared? A squared is 8q plus 3 squared. Then this becomes 64q squared. 2 times the first time times the second one, so it is 48q. And then finally 9. But look, instead of 9, I can write 8 plus 1, and between this one and that one and that one, I can factor an 8 out. Okay, what is left in the pair of brackets? Let me call it t, and then I have 1 at the end. So if a is of this form, which is one of the possible cases, I was able to show that a to power 2 is 8 times t plus 1. This means that the remainder of a2 by 8 is 1. And that is exactly what I wanted to show. But this is only one possible scenario. I have to consider 3 more. and then I am done. Is that clear? Because these are the only possibilities. If I have an integer, I have 8 possibilities. Now I know something more. I know that a is an odd integer, so it means that I have only 4 possibilities. For each one of these possibilities, I should do some simple algebra like this and convince myself that at the end 8 squared is a multiple of 8 plus 1, which is doable. It's not hard. If you write this, that's completely okay. But another rule is that sometimes it is good to be a little bit lazy. Okay? Because if I have given you this before, as soon as you see that a is an odd number, what do you write? Instead of considering so many scenarios, what do you write? You say that you are telling me n is odd, so I am allowed to say that a is a multiple of 2 plus 1. Everyone agrees that? So a is a multiple of 2 plus 1. Let me square it. What happens? It becomes 2q plus 1 totally squared. So this becomes the first one squared, 2 times the first one times the second one, plus the second one squared. But the point is that you see a factor of 4 emerging very clearly. So it means that it motivates you to factor a 4 out. Then it gives you q squared plus q, and then you have plus 1. And then if you call this one, for example, capital Q, then you have 4 capital Q plus 1. Yes? It is not wrong. It's a valid argument. What I showed that a to power 2 divided by 4 gives the remainder 1. It's a true statement, but unfortunately it is not the statement demanded in the problem. The problem asks you to show that if you square it and divide it by 8, the remainder becomes 1. Yes? Do you understand the problems? Okay. But we can actually find a very nice way out of it. How we can? Instead of here, so in principle, I want you to be observant. Usually, whenever you see the factor of 4, you immediately take a factor of 4 out and you call this q whatever you want to, and then you draw some conclusion which is valid, but unfortunately not in the problem. What is not, that's not demanded by the problem. But now let us, instead of factoring 4 out, do you have any suggestion? I can factor more things out, which usually is not useful, but in this case it is. So can you tell me what can I factor out here more than 4? More than 4, you say 2? Yes? Okay, so what can I factor out? Yes? Yeah, what can I factor between these two out? More than q. 4q. You're killing me. I don't know. What do you do on the weekend? I really don't know. Okay, so q plus 1, and then you have plus 1. Okay? Do you understand what I'm doing? I am doing this one, but how do you think this will help, this kind of factoring? Can I, if I decide to call this capital Q, it doesn't help me anything because it gives me again 4 capital Q plus 1. It is not wrong, but it is not what is demanded in the problem. But why do you think this factoring, which is on the one hand valid, I factored 4q out, why do you think this will now solve my problem? Yes?
Because since q is an integer, that means that either q is even or q plus 1 is even.
So it means that whatever you see here, even though you don't know if q is even or odd, but you know the product is even. Because these are consecutive integers. One of them is definitely even. And that is enough to show that this product is even. Yes? You don't, if you ask me, do you know q is even or odd? I would say no. But in any case, q times the next number is even. Yes? So if this is even, what does this mean? It means it is a multiple of 2. Yes? So instead of that, q times q plus 1, I realize this is the product of 2 consecutive numbers, so this becomes even. And then this 2 and that 4 will give me a factor of 8 that I need in this problem. So I told you that even though this is completely valid argument, but you have to do it in 4 steps. But here you just do it in 1 step and then just argue that why this part is even. So this method is more efficient here. But still I am using the division algorithm. But for even and odd, you really don't care about the name. When I say a number is odd, you immediately write it of this form. Yes.
Could you explain one more time how you got from 4Q to 18?
So I told you that if I factor 4Q out, this combination is definitely even if I don't know Q is even or odd. I tell you that if Q is even, then of course this product is even. If Q is odd, the next number is even, and again the product is even.
Yeah.
So this number that I have put in this circle thing, this is an even number. When this is an even number, this itself is a multiple of 2. Okay, and then this is a multiple of 2 multiplied by 4, it becomes multiple of 8, then I have 1 there. So this means that if I divide a squared by 8, the remainder is 1. By the way, this is acceptable as the remainder, yes, because it is between 0 and 8. Yes? So that is one. Another scenario, do you think 4 will also work? So I think this I will consider the simplest solution for this problem. This is also completely valid, but it is a little bit lengthy. Yes? But if you want to choose another number, here I chose 8, there I chose 2. What is another guess might be that's working? A good number that you have some kind of feeling that it might work. Yes? 4. Let us check. But in 4, how many cases should I consider? In 8, I considered 8 cases first. Because of oddness, I actually dropped 4 of them, so I have to work with 4 cases. But let us solve the problem choosing 4. The reason that I'm solving this problem from different perspectives, because I want you to learn the content of the theorem, okay? So, if I say A, and for some reason, comes to my mind that it is good to choose 4, then how many scenarios in total you have? You have 4Q, you have 4Q plus 1, you have 4Q plus 2, and then you have 4Q plus 3. Do I have something more? Yes or no? No. There's 4 cases. But I can immediately drop 2 cases, because 4Q is definitely even, but the problem A is odd, so I drop that. The other one is also dropped, yes, because 4Q is even. If you add 2 to it, that's also again even, but A is odd, so I just drop that one as well. So how many cases are there? 2 cases. So I have to consider 2 cases. If I consider 2 cases, I want you to understand it is completely done. So let us just do this one again. So A squared is, let us just do this one. The first one squared is what? 16Q squared. 2 times the first one times the second one, 8Q plus 1. Do you agree? And what do I need? I need a factor of 8. And I have it in front of my eyes, yes? Do I really need to care about Q here? No, because what I need is a factor of 8. I already have it. So I just factor 8 out, even though still I can factor 8Q out, yes? So I would write 2Q squared plus 1 plus 1. Then I call this capital Q, then it is 8Q plus 1, I am done. But I want you to understand this is not the whole story, because there is another case to consider. Yes? So let me just do that one as well. A squared is the first one squared, 16Q squared. 2 times the first one times the second one is 48Q. And the second one squared is just 9. Yes? Remember, you need a factor of 8 out with the remainder 1. This immediately, by the experience you have so far, what do you write for 9? You just write 8 plus 1. And between this and that, you have your factor of 8. 24, thank you. Sorry. Yes. And then anyway, still I have my factor of 8, that's the good point. Between this one and that one and that one, I only need to factor 8 out, so this becomes 2Q squared plus 3Q plus 1, yes? And then I have 1 at the end. I can call this 1Q, and it becomes 8Q plus 1. I also consider this is a good solution. It's not that lengthy. I only needed to consider 2 cases. Yes? But the best solution, I agree, I hope that you agree with me, is just considering this one. But it needs a little bit of reasoning at the end. Yes? But here you don't need to be, you don't need to do some kind of smart reasoning or whatever like that. You just see your factor of 8 in front of yours. Yes?
How would you initially decide that?
There is no way. You have to solve a lot of problems. But my point in this course is not to if you are interested, you can solve harder problems. But I want you to understand the logic behind that. For example, if someone asks you, this proof is valid, you have to understand, yes, this is valid. Why this is valid? Because by this theorem, I have 4 possible cases. That's it. 2 of them cannot happen for this problem, so there are 2 left. If I can show you that for these 2 cases I am done, it is done. I want you to understand the logic is not ill. Yes, is that clear? That's it. But because I told you that these questions might be sometimes very hard. Okay, let me see if I can give you another example. So by the way, this is a good result, you know. For example, if you have an odd number, when you square it and then divide it by 8, the remainder becomes 1. So the conclusion is that if you have an odd number which is not of this form, it is not a complete square. Yes. So if you have an odd number whose remainder by 8 is not 1, then if you want to, you can conclude that that number is not a complete square. Okay, so let me give you another example. Wait for you to solve it for me. Okay, I want you to prove it. A is an integer, any number that you like. I want you to prove that 3 divides a squared plus 3. Yes? No, plus 2, sorry. A squared plus 2. So this is a good question. It's simple. But if you can solve this problem on your own, it means that you really learned what I told you. Yes? So I wouldn't say that this is a very hard problem. Any number that you choose, show that this combination happens to be a multiple of 3 for all cases. Okay? Okay. Is there anyone who wants to tell me what to do here? Just guide me and I will write whatever you say to me, okay? So what should I write here? So you know that this is an example for the division algorithm, these type of problems. So you need to have a choice for that B. Which one is natural here to choose? 3 is probably the most natural one, yes? Because you want to prove the division by 3, yes? So then as soon as you realize this is your strategy, then the next step is easy. So what is the next step? You would say that A belongs to Z. So this means that there exists a Q in Z so that A is 3Q or A is 3Q plus 1 or A is 3Q plus 2. No other options available for A. Exactly one of these things should happen for A. If I can show this is true for all these scenarios, then I am done. Yes? That's a very simple exercise, I would say. So what you say that, okay, case number 1. If A is 3Q, then this means that A times A squared plus 2 is equal to. Instead of A, I put 3Q, so this becomes 3Q. This becomes 3Q squared, which is 9Q squared. And then plus 2. But don't get lost. What was your strategy? Your strategy is to show this right-hand side is an integer multiple of 3. Do I have it here? Yes. Because this number is definitely an integer, yes? So this is done. So in this case, this combination is a multiple of 3. So in that case, 3 divides that. But this is not the whole story. There are 2 more. steps. Number 2. So what should I do now? I have to do the simple algebra again, but for this one. So then I would say that if a is 3q plus a 1, this implies that a times a squared plus 2. You have to be a little bit patient of this simple algebra. Instead of a, I put this combination. This becomes 3q plus 1. And then a squared. So let us just do it in our head. We want to raise it to power 2, so I have to use the squaring rule. So the first one squared is 9q squared. 2 times the first one times the second one is how much? 6q. Okay? The second one squared is 1, but there is another 2 added to it, yes? So if I raise this one to power 2, 1 plus 2, it becomes 3. But what is my goal? My goal is to make the factor of 3 transparent, yes? So, and that, is it any one that I can factor? Yes. Fortunately, between these 3, I can factor a 3 out, yes? So the 3 goes out, then I will have 3q plus 1, and I will have 3q squared here, plus 2q, and then plus 1. Again, am I sure that this is an integer? Yes. So that's also an integer. So this is also the same story. This means that 3 also divides a times a squared plus 2. Understandable? So there's only one option left, one possibility left, and that is number 3. So let me write it here. So number 3, if a is 3q plus 2, okay, and then what happens? This means that a times a squared plus 2. Let us do some simple algebra here again. Instead of that, I put 3q plus 2. Might be I have done something wrong. Does it work or not? Yeah, it is written that it should be the case, so there are no exceptions. Let me choose. Let me see what we can get. So now this one is squared. I want to do it in my head, but remember at the end I will add a 2 to it. The first one squared is how much? 9q squared as before. 2 times the first one times the second one is 12. 12 what? 12 q. This one to power 2, remember, is 4. But there is a 2 coming in, which will be added to what? 6. So and then again you have your factor of 3, yes? Because between these 3 now, you are fortunate and you can factor a 3 out. If I factor a 3 out, so it becomes 3q plus 2, and then I have 3q squared plus 4q plus 2. And hopefully you agree that even in this case, whatever this is, it's an integer. And then again, it means that in this case, I can also conclude this. But the point is that because of the division algorithm theorem, these are the only possible cases, and I was able to show this for all possible cases. This means it is done. I want you to understand, if I ask you to solve this problem before teaching you this, I don't know if is there any other way that you can think about, even though the problem is very simple. It is telling you that whatever you choose for a, this combination happens to be divisible by 3 all the time. But I want you to understand that this is what is necessary. This is a real mathematical proof. This shows that we have only 3 cases for a, and in each 3 case I was able to prove this one, and then I am done. Yes, which was not that trivial. So there is an example in the book. I want to solve that one, and then I will probably stop. They have talked about this problem in the very first part, and then if you see the solution, it is the solution exists in the book. They are using division algorithm without mentioning it. Okay, so the question is actually interesting. So let me just give you the number. I don't follow exactly the words there, but I want to introduce. This is problem 1113. It's a level 3 problem, yes? So 1113, Matematik 5 Origo, yes? Okay, so let me just give you the content of that problem. in the problem they are talking about, if I understand the Swedish correctly, they are talking about a twin prime. Yes, what is a twin prime? So let me just write some of the prime numbers. The first number is 2, the second one is 3, the second prime number. The next one is 5, 7, I don't know. The next one is 11, 13, and continues. So you see, this is the only even prime number. And then this is called a twin prime. The primes that differ exactly by 2 is called a pair of twin primes. So for example, 5 and 7 is also a pair of twin primes. They differ by 2. This is the definition of twin primes. Yes? Okay, now the one part of the question is to list all twin primes before 30. Okay, so let me just continue my list. So 13, and then what is coming next is 17, and then 19, and then 23, and then after 23, 4, 5, 6, 7, 8. No, 27 is not prime. It's divisible by 3, so 29. Yes, so this is the list of prime numbers less than 30. So in the part 1 of the problem, you want to find all twin pairs in this list. So what are the twin pairs? One pair is 3 and 5. Yes? Pardon? No, the 2 counts, but the difference is 1. I want to have the difference exactly 2. Yes? So 3 and 5 is one pair. Yes? 5 and 7 is another pair. And then 11 and 13 is another pair. 17 and 19 is another pair. That's it. Yes? So these are the only twin pairs in this list. Yes? And then what is the difference between these two prime numbers? 1. Yes? Now my question for you before solving the problem. Do you think it can happen again that we have two prime numbers which differ exactly 1 unit? So you see, this is not possible. Yes? Because if they are supposed to be consecutive ones, one of them should be even according to division algorithm, and the even one cannot be a prime number because there is only one even prime number, and that is 2. The reason is that other even numbers are divisible by 2. Okay, now there is a very interesting question here. If you look at this triple here, this differ by 2, this one also differ by 2. So 7 is 2 units larger, 5 is 2 units larger. Do you think, the interesting question is this. Do you think that this can happen somewhere in this list if you continue forever? Do you think you will be able to find 3 prime numbers so that they have this situation that the middle one is 2 units larger than the left one and is 2 units less than the other one? So I want you to understand this is a very non-trivial question. Because if you ask me, do you know the list of prime numbers? We don't know even what are the list of prime numbers. But we want to convince ourselves in one way. So if you think there is, you have to give me another example. If you want to show me, no, there are no other triples like this, so then you need to have a good reason for that. So the problem is asking you to show that this is not happening. It will not happen in this list. That you have this situation that one of them is 2 units larger than the other one, and the third one is 2 units larger than the middle one. So I want you to understand that this is a very non-trivial question. It doesn't mean that it is very hard to answer. Yes, but it is non-trivial. Okay, can you tell me why there are no any other triples of that size? And that is the content of the hard part of the problem, which is level 3 problem. Yes? Okay, so because there is no time left that much, let me just solve it for you. So I want to show that 3, 5, and 7 is the only triple with that property. Okay? So let us say that this is not the case, and then P, you have this scenario later on. if you have this scenario later on, p is a prime number, the next one should be p plus 2, and the next one should be p plus, if this is going to happen somewhere down the list. So the first one is a prime number. If it is going to happen something like this, the next one should be plus p plus 2, and the next one should be what? P plus 4. Yes? Okay. This is the case. Let us see if this is going to happen or not. P is an integer. Yes? So P can be written in one of these three cases. 3 times k. So let me try. Right. 3 times q, or 3 times q plus 1, or 3q plus 2. This is inevitable. When you say p is an integer, you have to admit that p is one of these. Yes? But 3q is not possible in this case. Why? Yeah? Yeah. Because p is supposed to be a prime number. This tells you that p is a multiple of 3. The only multiple of 3 which is prime is which one? Is 3 itself. And in that case, yes, it happens. 3, the next one is 5, the next one is 7. We know that. So now we know that p is a prime number larger than 3, because we already considered 3 and we know that there is a triple of that type. But so let us assume that p is a prime number and larger than 3. So this means that this cannot happen for a prime number. Is that clear? So there are two other scenarios going on. Either p is 3q plus 1, or p is 3q plus 2. If p is 3q plus 1, then the first number in my list is 3q plus 1. The second number in my list becomes 3q plus 3. And the last number becomes 3q plus 5. Yes? But then look, the middle one is no longer a prime number because it's a multiple of 3. If this happens, what happens? Then the first number is 3q plus 2. The second number is 3q plus 4. And the last one becomes 3q plus 6. And then what happens? The last one becomes a multiple of 3, and it cannot be a prime number. So let me just finish this one, because I want you to understand the logic. Can I say this is not a prime? No, 3q plus 2 might be a prime, might not be a prime. I don't know. For example, if I choose 1, it becomes 5. If I choose 2, it becomes 8. So I cannot say that this is definitely not a prime because I don't see it's a factor of anything. Yes? Because you don't know anything about q. But one thing is clear. This is definitely not a prime number because it's a multiple of 3. This is definitely not a prime number because that's also a multiple of 3. So this simple argument, I want you to understand, this problem looked very, very hard. How we want to convince ourselves that this cannot happen down the list forever, if you continue forever. But we were able to use this idea of the division algorithm to actually understand this quite well. Yes? Is that clear? So that is the solution of this problem. Yes?
But something questionable was that R, you said earlier R could only be less than 3. But there you can see that 3q plus 5 is more than 3. Like R and B, right?
No, well, I agree with you. But then this you can write it as 3q. And then instead of write, we can 3 plus 2, and then factor a 3 out and write it like this. But it doesn't matter for me. No, it doesn't matter. Here, what I care is to show that one of them is not prime. Any number of the form 3q plus 5 is also 3q plus 2. But the point is that one of them is not a prime number. So this means that this situation is very unique for prime numbers. Even if we don't know them, but we know that this thing will not happen ever again. That I have 3, I don't know, something like twin primes consecutively. Yes, that is a unique position among prime numbers. And you see that it's a hard problem, but the solution is very simple, and I think it's a very good example to show that how we can use division algorithm, because it seems very trivial, but this is a highly non-trivial problem that we are answering using division algorithm. Yes? Okay, so I think we are finished with this division algorithm, and then the next part is the most exciting part of number theory, and that's modular arithmetic. So we will actually go to that one, and then we go to the next lesson. Thank you very much.